us continue with the mixed volumes. So today I will finally define what mixed volumes are, but before let us look at the proofs, solutions of some of the home exercises. So there was this theorem that the integral, that the volume of a body K with a smooth boundary is equal to 1 over d, the integral over the boundary of K, the support function. So somehow the support function now I'm a bit confused because somehow the support function is not defined on the. Yes, actually the formulation of this theorem was not completely correct because the support function is defined on the vectors in the space, not on the boundary of the body. So what one has to do is to take the boundary of the body, then send it by the Gauss map to the sphere, and then take the support function of the sphere. So actually what is written here is the support function composed with the Gauss map. So it's the Gauss map by gamma, H composition gamma, the area. So this is the area element on the boundary. It's gamma. The boundary of K goes to ST minus 1 is the Gauss map. So the proof of this formula is as follows. Let us take the following function defined on RD, which sends x to the squared norm of x. And this function is very good because the Laplacian of the squared norm, what is this? So we take the second derivations of this, and we get each time 2, because the second derivative of xi squared is 2. So the Laplacian is equal to 2 times d. Good. And now let us integrate this function. Integrate it over the body K. So on one hand, since this is just a constant, 2d, what we get here is 2d times the volume of K. Okay, so the 2d times the volume of K is this integral. Okay, now here we have the Laplacian, so perfect, we can apply the divergence theorem and get the integral over the boundary of K of the gradient of the inner product of the gradient of this function with the outward unit normal. Right? And then this is equal to what? The gradient of the norm squared is twice the vector x. So we get 2 times the integral of the boundary of K, x inner product with n, the area. And I claim that this is exactly the support function, well, composed with the Gauss map. And this is because of the following picture. So if this is our body K, and we have a point with the outward normal n, and somewhere here we have the origin, then so the support function is this distance, right? And this distance is equal to the scalar product of, so x is exactly the point here, the point on the boundary of K, right? And if we take the inner product of this, of the position vector of this point with n, then what we get is exactly that distance. So this xn is equal to the support function at the vector n, and n is, well, this is exactly the Gauss image of the point x, h of gamma of x. And this finishes the proof of the formula. Then one can prove the other formula, so which was the integral of the integral of n, the area equals 0 with in a similar way, but one has to take, instead of this function, an arbitrary linear function. So take f of x equal to w in the product x. Then Laplacian f is equal to 0, and then one can continue in a similar manner and get a proof of this formula. Okay, then there was the formula, the two discrete analog of that, and the first one was, so I explained how to do it with the pyramids. And the second one, which was the sum, no, let me write it here. So the sum hi, no, there was no hi, it was the sum of the areas of, well, the d-1 dimensional volumes of the facets multiplied with the normals of these facets. This can be proved by taking, so this follows from the formula for the volume that we have proved. Volume of K is 1 over d, the sum hi d-1 dimensional volume of Fi, and from the fact, well, so in this case I used the notation P because I was speaking about the polytopes here, and from the fact that the volume does not change if you translate the polytope by, let me put here vector W. So if I translate the polytope P by a vector W, then the volume doesn't change. So one can apply here the same formula, and one has to look at how the support numbers change. And if one makes these computations, then one arrives at this formula. And so here one has to continue, and then these formulas are proved. So then what we are doing today, today is one of the most important lectures in this, so in my mini course. So because first I will define mixed volumes. And then I will state some inequalities about mixed volumes. Good, so if we have a convex body K, then we can scale it by any non-negative factor. So if I define lambda K as the set of lambda x over all x in K. If you have two convex bodies K and A, then we can form the Minkowski sum. So the set of x plus y, x from K, y from A. But that means we can also take any collection of convex bodies and then consider a sort of linear combination of these bodies, but only with non-negative coefficients. So then lambda 1 K1 plus so on plus lambda n Kn makes sense for non-negative lambda i's. So this positive or non-negative combination of convex bodies makes sense, and what we want now is to compute the volume of this combination. And this is a theorem by Minkowski. And it says that the volume of this linear combination is a polynomial in the coefficients of the combination. Namely, it is a polynomial, it is homogeneous polynomial of degree d. How can you write an arbitrarily homogeneous polynomial of degree d? So this is the sum of, so the coefficients, so you have to choose any d lambda i's, and it is possible to repeat them. So you choose any indices I1, so on, ID. So they range from 1 to n independently. So they can all be equal to 1, for example. And then we put here an coefficient A, I1, I2, so on, ID. And the monomial lambda I1, lambda I2, so on, lambda ID. So that's the theorem. The volume is a polynomial. So there are some coefficients which depend on the bodies K1, so on, Kn. And once these coefficients are determined, then for any lambdas, the volume is equal to that expression. So let us play a bit with this statement, because it is very general and not very appealing at the first sight. In fact, one can see it as sort of a multinomial formula, because so one should look at this as, well, so this is similar to taking just the dth power of this linear combination. So we write lambda 1 k1 plus so on plus lambda n kn to the power of d. And if you want to expand this, then what you usually get is, I mean, what you always get is the sum of, so you have to take, so you have d brackets, right, one after each other, and you take a summand from each of the brackets. So what happens is that you get the sum of these monomials multiplied with some product of ki's. So this is the sum of lambda I1, lambda in, ki1, kin. And this is sort of a formal product of these bodies. ID. Sorry. So this is not in, this is ID. This is ID because we have power D. Okay. These coefficients, they are called the mixed volumes. But one has to do one more thing here, because in fact the coefficients are not completely determined by the function. Because so if one requires that the coefficients are symmetric in the indices, then they are uniquely determined. So it is like having a bilinear form. Well, a bilinear form can, and making a quadratic form out of a bilinear form. If a bilinear form, and from a quadratic form you can go back to bilinear form, but there are different bilinear forms for the same quadratic form. But there is only one symmetric bilinear form. So that's sort of, the symmetry assumption determines the coefficients uniquely. So, and this is how the mixed volumes are defined. So under assumption, or under requirement that that A, I1, ID are symmetric, under permutations of indices. I mean, symmetric are invariant under permutations of indices. They are called the mixed volumes. mixed volumes of our bodies K1 so on Kn, and the notation is that AI1 ID, this is the volume of Ki1 Kid. So that means in this multinomial expansion, so what is happening here, you have not, so this formal product of bodies, this is the mixed volume of these bodies. And we, by definition, we require that the mixed volume is symmetric. If you permute here into bodies, then the mixed volume doesn't change. All right. Good. So let us look at. So in this case, there is d, which is the dimension, and it's always fixed, and n is variable. N can be any number. It can be smaller than d. It can be bigger than d. One special case is n equal to 2, and in this case we have volume of. So what is a good notation here? Let us take lambda k plus mu L. Then by this theorem, we have not proved it yet, but if you prove it, then a special case of this theorem is the following. So here we sort of take lambda k plus mu L to the power d, and we know, so everybody knows what it is. This is the sum of d choose k from 0 to d, lambda to the power k, mu to the power d minus k, and here we have the volume, mixed volume of, so we take k times the body k and d minus k times the body L. So now I need more place for this formula. K times, and then L d minus k times. By the way, there is a convenient notation in order not to write this. One can write volume, and then here I write in the brackets how many times I am taking the body k, and then how many times I am taking the body L. So this is notation, shorthand notation for that. Good, but now that reminds very much the Steiner formula. And in fact, yes, Steiner formula is just a special case of Minkowski theorem. In the Steiner case, what we have is L is the ball, and we just put lambda equal 1. So of course in this formula we can substitute lambda equal 1. And I remind that the R neighborhood of any body k is equal to k plus RB. So what we have is volume of k plus RB is equal to the sum k from 0 to d, d choose k, and then so we have, so one has to decide for k or for d minus k. So I take k times, well, I want to have r to the power k, therefore I must take d minus k times k and k times b. That means I take the mixed volume with d minus k copies of k and k copies of b, and this gives me r to the power k. Right, so each r is associated with b. Good, but we had the Steiner formula in a similar form. It was also the sum with a binomial coefficient here, but this term was denoted by wk. So our wk, so the squared mass integral. Yeah, so that was the notation that I'm saying. this line. This line. Yes, right. So this was the definition. I will give an example, but somehow the definition is quite short. But well, so to digest it, one needs to look at the examples. The definition is just well. So if the theorem is correct, and in special cases one can see that it is correct, then these coefficients, they are called the mixed volumes, and they are denoted. Yes, so actually, the mixed volume is defined as the coefficient in that expansion. So this is what is happening. And one important special case is the Steiner formula. In that case, we just have a combination of two bodies, and also one of the coefficients is just equal 1. And then with our new notation, so our new notation is then, we had also some old notation because these coefficients were denoted by WK. So WK of K is equal to, so I'm confusing here K and T minus K quite, but according to my notes, and I think that's, so exactly, we had WK r to the power K, so therefore WK of K is equal to the mixed volume of D minus K copies of K and K copies of the ball. So we have two notations for the same thing now. Good, so let us compute the mixed volume of two bodies. And then after that I will prove the theorem. Actually the proof is not so difficult. So this is the situation where it's more difficult to understand the statement of the theorem and actually later to prove it. Let me leave it here, and so we take the dimension D equal to 2, and we take very simple two convex figures, so namely two rectangles. So I take one rectangle scaled by lambda, add another rectangle scaled by mu. So I assume that the sides of this rectangle are A1 and B1, and here the sides are A2 and B2. So this is my lambda K plus mu L. So what is this then? So I get a rectangle with side lengths lambda A1, lambda B1, and another rectangle. Then I get a bigger rectangle as the sum with side lengths lambda A1 plus mu A2 and lambda B1 plus mu B2. And in this case, it is easy to see that the theorem holds, that the volume, the area in this case, the area of this is a polynomial in lambda and mu. And so we can even compute the mixed area of these two rectangles. Okay, so the two-dimensional volume of that, so this combination, lambda K plus mu L is equal to the product of the side lengths, lambda A1 plus mu A2 times lambda B1 plus mu B2, which is equal to lambda squared A1 A2 plus A1 B2 plus A2 B1 times mu plus mu squared B1 B2. Now we look at this formula. So we have indeed a homogeneous polynomial of degree 2 in lambda and mu. Yes, that's A1 B1. And here it's A2 B2. Thank you. so it works. One has to make mistakes and then yes, but yes, thank you. So the coefficients are the mixed volumes, and so this coefficient is somehow the mixed volume of K with itself. But well, it's just the volume of K, right? A1, B1. This is so that if you, that's also very natural. So if you mix, if you don't mix, so then you just get the volume itself. And the same here, and here we get a very nice formula, namely the mixed area, in fact, mixed area of K and L is equal to 1/2 A1B2 plus A2B1. One should not forget 1/2 because, I mean, so we have this, somehow we have here, so we have products of K and L in two, as K times L and then L times K, and this accounts for this, actually this coefficient must be divided by 2. So what we do here, we multiply the width of the first with the height of the second, and then we add height of the first times the width of the second. So that's exactly mixed area. So we mix the 2 dimensions. So we mix two rectangles. All right, and then it's also logically, well, quite natural to take 1/2 because so here is one area, here another area. If by chance they coincide, these two rectangles, then of course the area must be just the usual area of the rectangle. Okay. So then, as for the mixed volumes of K with B, we have already seen what they are. Again, so I have done this picture here. I can draw it here again. The coefficients in the Steiner formula, they have very simple geometric meaning in the case of polytopes, and so this is somehow the coefficient at lambda squared, and this is the coefficient at lambda, and similar things happen in higher dimensions. Good. So it's maybe, I mean, I would like to prove the theorem, but maybe I will not. Okay, so just a sketch of the proof. So first, it suffices to prove that for polytopes. It is exactly like with the Steiner formula. We proved it for polytopes, and then by approximating any convex body by polytopes, we got the general case. And for polytopes, we take K, we denote by K this combination. And then we take the formula for the volume of K, which is 1/d, the sum of, so that's exactly the formula that was given last time, but I want to change notation now because the other notation is better suitable for the proof. So this is the sum of H sub K of Vj times the d minus 1 dimensional volume of Fk of Vj. The sum goes over all j from 1 to m, and what is Vj? Vj's are the normals to the facets of K, and well, then Hk is just the corresponding distances, Hk of Vj, and Fk of Vj is the facet, so the top dimensional face of K. So this is Fk of Vj. So that's the same formula, but I have written now it with different notations. And then one has to expand. So what is Hk of Vj in terms of Ki's? In terms of Hki of Vj, and also the volume d-1 of fk of Vj in terms of the volume, well, in terms of actually mixed volumes, because what is happening then, we are proving it by induction. So, induction on the dimension d. And then, so since this is a sketch of the proof, the sketch can be ended at any point. All right. Then there is another very important formula. So for any two convex bodies in RD, the mixed volume where we take d-1 copies of K and only one copy of L is equal to 1 over d, the sum over, well, since I now use the index j, let me use index j for the list of the facets from 1 to m. Okay, so I want to take somehow this formula, the sum of support number times the phase area, and mix my K and L. And the support numbers are of degree 1, and the areas are of degree d-1. That's very good. So let me take the h of L and the areas of the facets of K. So the sum here goes over all normals to the facets of K. All facets of K. So this formula looks very natural again. So because we have here K taken d-1 time, L taken once, and so here L comes somehow with degree 1 and K comes with degree d-1. But this does not follow directly from the definition of mixed volumes. So somehow remark. What follows from the definition of mixed volumes, if one does that proof carefully, well, from the above argument, so that from the above argument, so which remains not complete, what follows is that this mixed volume, well, actually, so here so that's the situation where it's useful to put index in the volume, because this volume and that volume, these are two different volumes. So the mixed volume of d-1 copies of K, 1 copy of L is equal to the following thing. This is 1 divided by d times d-1, and then there comes this expression but there is also another sum here, namely we must take d-2 times the sum of a j from 1 to m. Now we take hk of Vj and take the mixed volume of d-2 copies of K and 1 copy of L. So we take the mixed volume of f K of Vj So let me write this in my shorthand notation: d minus 2 copies of fk of vj and 1 copy of fl of vj. This formula is also natural, and actually it follows directly from the argument. Why it is natural? It's because what we have is 1 copy of L, and the rest are K's. In what ways can we combine them? So we can use L in this linear term, but we can also use L here inside the volume of the facet, and we do it. So we use it here once, and then so the rest is K. And this formula does not imply that. So what we have to prove is that this sum is equal to that sum. And one will have a lot of problems if one tries to do it directly. What one should do instead is to forget this formula and look at this again. Now remember what is this? What is actually this mixed volume? So I will also try to remember what is this mixed volume. Yes, what we have is the volume of K plus lambda L is equal to volume of K plus D times the mixed volume of D minus 1 copies of K, 1 copy of L times lambda, and plus O small of lambda. So that's just the mixed volume, so this expansion of the volume, right? So just here I have written volume of, it is volume of K, right? So here it's volume of K, L. And here we have coefficient lambda, and later we have lambda squared, lambda cubed, and so on. So this implies that this mixed volume of D minus 1 copies of K, 1 copy of L, this is the limit, this lambda goes to 0, volume of K plus lambda L minus volume of K divided by lambda. And now this is what one should look at. And if one looks at this and draws a picture, so namely one has to compare this body with that body. And then if one draws the picture and looks at the picture, then one comes to this formula. So actually this other formula, it was not useful now, but having proven this, we can derive that actually this sum and that sum, they are equal. So it does not matter in what way you mix the bodies. It is all symmetric. You can use your L here, or you can use your L inside the facet areas. So this formula is interesting anyway. I think, in fact, it's also used later in proofs of some inequalities. I don't think that we come to really to the proofs of the inequalities, but at least I will state them. And at least also we have here a nice and useful tool for doing things. Also, in some way, this formula is dual to the Schlafly formula. So that's I can only say that, so I cannot speak about the Schlafly formula, but for those who knows it, it's okay. So now the second part, inequalities. Alexandrov, well, just inequalities, and then I will give the names. First is the Alexandrov. So that's that AD Alexandrov. Fenchel, that's the Fenchel from Fenchel-Nielsen. But here they did something completely different. So let KL, then M1, so on MD minus 2 be convex bodies in RD. Then the following holds. If you take the mixed volume of K, L, and all these MIs, so inside the mixed volume there are always D arguments, because volume is sort of polynomial of degree D, right? Volume is D homogeneous, but each of the arguments enters linearly. So I haven't proved that, but that would be somehow next lemma after the introduction of the mixed volumes. So volume is actually a multilinear function. I mean, volume is a homogeneous function of degree D, but from any homogeneous degree D thing, you can make a multilinear thing. That's actually the content of the Minkowski theorem. All right, so now the inequality, if you take this volume squared, then this is bigger or equal than the product of volume of K, then all MIs, times the volume of L, and then all MIs. So that's sort of inverse Cauchy-Schwarz, or I forgot the name. So it's like, since this is a multilinear form, if I keep these MIs fixed and concentrate only on two arguments, this is actually a bilinear form. So what is written here is Q of KL squared is bigger or equal than Q of KK times Q of LL. And if this bilinear form would be just the inner product, well, let me take inner product of two vectors VW, then VW squared is, it is less or equal than V times WW. So this is the well-known inequality, and this is the less well-known inequality, and it also goes in the other direction. Then, so the proof of this inequality is quite complicated, and I would like to give the proof, but it just, I will give a reference to some recent work where it is proved in a nice way. Then there is the second Minkowski inequality. This is, in fact, a special case of Alexander Fenchel, namely the volume of KL squared is bigger or equal than the volume of K times the volume of KLL. Well, so if one compares with that, then one can see that this is a special case. But in fact, usually this is proved first, and then it is used as a lemma in the proof of Alexander Fenchel. Also, by the way, so since we have an inequality, it's interesting to look at the equality cases. So here the equality cases are known but quite complicated. Equality case. Well, if K is equal L, but not only, but that's, I mean, not necessarily condition. Sometimes K can be different from L, but there is still equality. The equality case known but complicated. And in the Alexander Fenchel inequality, equality case is unknown. I think, but I'm not sure, the equality case is known for polytopes. So if one assumes that these are polytopes, then one can describe the equality case. And then, so I start with the second Minkowski inequality. The first Minkowski inequality is again we have only two bodies K and L, and we take this volume, and it is to the power D. It is bigger or equal than the volume of K to the power D minus 1 times the volume of L. And here it is quite easy to remember the exponents, because again, so on the left hand side we have something linear in L, then to the power D. So this is of degree D in L. On the right hand side we also have something of degree D in L, because volume has degree D. And well, actually, it's again, I'm going now in the inverse order, because first Minkowski inequality is somehow easier than the second Minkowski inequality. But from the second Minkowski inequality, no, actually from the Alexander-Fenchel inequality, one can prove the first Minkowski. So Alexander-Fenchel imply first Minkowski. And this proof is actually meaningless, because one cannot prove it like that. One proves it in some easier way. But just in order to get a little bit used to this, let us see how does it imply. So let us introduce the following numbers. So let Vk be equal to the volume of several copies of K and several copies of L. Let me take D minus K copies of K and K copies of L. Then by Alexander-Fenchel, well, by Alexander-Fenchel, Vk squared is bigger or equal than Vk minus 1 times Vk plus 1. So for that one just takes all those mi's and somehow puts it equal to K or L. So this means that, so one also says for that the sequence Vk is log concave. Is logarithmically concave. So that's exactly by definition this inequality, and why it is called logarithmic concave, because that means that logarithms of these terms, they form a concave sequence. So because we can write this as logarithm of Vk is bigger or equal than 1/2 logarithm of Vk minus 1 plus logarithm of Vk plus 1. Okay, so let us take this inequality in this form, and let us see what has to be proved here, so in the first Minkowski inequality. The first Minkowski is equivalent to, in our new notation, this means V1 to the power D is bigger or equal than V0 to the power D minus 1 times Vd. Okay, but now if we take logarithms, then this is equivalent to log V1 is bigger or equal than 1 over D, D minus 1 times log V0 plus log Vd. But well, so that's, this inequality is implied by these inequalities, because this somehow just says that if you take the, somehow construct the diagram of these logarithms of volumes, then it looks like that, because locally it always makes this turn. But if it makes this turn, then of course, so this volume V1 and the volumes V0 and Vd, they are related by that inequality. So somehow local concavity implies global concavity. So all these inequalities, they are somehow very closely related. So first Minkowski, second Minkowski, and Alexander-Fenhiel, this is all, they are all from the same place. What I want to do in the remaining 7 minutes, I want to come back to the Quermass integral, so to the Steiner formula, and see what does this give. So we had the Steiner formula now in several different ways, and we have written it in several different ways. So one is, so let us take dimension equal to 3. Then the volume of Kr is equal to volume of K plus, what was next? R times the area of the boundary plus R squared times S of K plus R cube, and what is there, it's just 4 pi over 3. Okay. So that was what we taught in the first lecture, and then we have also written it in, thank you, as follows. This is W0 of K plus 3 times W1 of K times R plus 3 W2 of K times R squared plus W3 of K times R cube. In these Wi's, today we have seen that Wk of K, this is just the mixed volume of D minus K copies of K and K copies of the unit ball B. Right. Good. So now for this Wk of K, we have these, so the same inequalities as here, because, well, so what I denoted here by Vk becomes Wk if I substitute instead of L the ball B. So we have then from the first Minkowski inequality, for example, so Minkowski the first implies that, for example, it implies that, what does it imply? It implies that okay, I just write what I have written, and you can check that this is indeed. So the area of the boundary of K to the third power is bigger or equal than the volume of K squared, and then multiplied by 3 divided by 4 pi, no, by 4 pi divided by 3. So this is somehow, this is W1 cube. Now I'm checking with myself, W1 cube equal then W0 squared times W3. And this is the isoperimetric inequality. And also the equality case, it's important. So in this case, the equality case is very simple. In the first Minkowski inequality, equality occurs only if K and L are homothetic. Equality if and only if K and L are homothetic. So in this case, since L is the ball, the equality occurs only if K is a ball. So that's then the proof of isoperimetric inequality from these inequalities from mixed volumes. But from the first Minkowski inequality, one can also derive that now changing K and L, so exchanging K and L, one can derive that W2 squared is bigger or equal than W3 times W0 squared. No, W3 squared, W2. No, here it's third degree. Now it's correct. Because 2 times 3 is equal to 3 times 2 plus 0. And this inequality means then, if one goes back to these definitions, okay, so this can be written as the width of K divided by 2 cube is bigger or equal than 3 divided by 4 pi, the volume of K. W of K is the average width of K. We know that the average width is proportional to W2, so to this S of K coefficient. And you remember, so this S of K, this was the sum of edge lengths times the angles or the integral of the mean curvature. So here the equality occurs only if K is a ball, and for the ball it's easy to check that that's correct, right? So the width of the unit ball is equal to 2, so that we have here 1, and here we have the volume is compensated by this factor. So that's not an isoperimetric inequality, but something else. So that is, the volume has the smallest average width among all bodies of the same volume. And this inequality is called Orison inequality. Orison was a mathematician who died very young, and he did actually many well-known things in the general topology. But aside from that, he also proved this inequality. So these are consequences of the first Minkowski inequality, and we can also look at what follows from the second Minkowski inequality. And maybe that's, yeah, so let me write this, but then you should check by yourself that these are really consequences of the second Minkowski inequality. So the area of the boundary of K squared is bigger or equal than 3 times S of K times the volume of K. Well, this is not very exciting maybe, but it relates 3 quantities at the same time. Another inequality is S of K squared is bigger or equal than 4 pi times the area of the boundary. So from second Minkowski, one can derive these two inequalities. So the plan for the next 3 lectures is more or less, I am going to prove the so both Minkowski inequalities. So Minkowski 1 and Minkowski 2 will be proved. So without the equality cases anyway. And for the Alexander-Fenhiel inequality, I can recommend the recently appeared in this year article by Schoenfeld and handle. Maybe let me very quickly find the exact title. No, that's one handle, but a different paper. Yes. Mixed volumes and the Bochner method. So I will speak about that, but I will have no time to speak about this. And then, so this I will probably do tomorrow, and then after the break of 2 days, I will go to some, to speak a little bit more about Alexander Fenhill and about some discrete Laplacian operators and something like that. Okay, then that's it for today.